In this section of Chapter 13, we're going to look at catalytic hydrogenation. So with catalytic hydrogenation, we're going to convert pi bonds to sigma bonds through a reduction process using H2 and a metal catalyst. Some common metal catalysts are palladium, nickel, palladium mixed with carbon, platinum oxide, and platinum. This is going to be a reduction process and not really involve an electrophile with our hydrogen, but it has a similar mechanism and can be useful synthetically, so the textbook covers it with all of our other alkene reactions. So let's look at the reactions with our alkene. So initially we're going to start with our alkene, and we're going to put it in the place of hydrogen gas, and we're going to deal with some form of our catalyst. So what we want to recognize here is that these catalysts are going to be heterogeneous in nature. We have our alkene, which is typically going to be a liquid. We have our hydrogen, which is in the gas state, and then we have our catalyst, which is a metal, so it will be a solid state. So we see these heterogeneous catalysts where we have different states of matter. So we have to find ways to make sure that they all interact together and make sure we have a high surface area interaction between all three of our different phases. Through this process, we are going to get rid of the pi bond, and we are going to add hydrogens across that pi bond. So we no longer have the pi bond, but we have our sigma bonds, so all single bonds. What you do want to recognize with this addition is that those hydrogens are going to add across the alkene in a syn addition, meaning both hydrogens are going to be on the same side, and that will impact our stereochemistry if we have stereocenters in our process. So let's look a little bit at our mechanism. It is a very different mechanism because of the heterogeneous nature and the use of the catalyst that we have. So we're going to have our metal catalyst, which I'm just going to denote with a square rectangle. We're going to see that the hydrogen is going to adsorb to the surface area of our metal catalyst. At the same time that is happening, our pi bond is also going to interact and adsorb to our metal catalyst. So this will interact with, again, the surface area, which is why we have to make sure we have a very high surface area when we run these reactions. So now that everything is adsorbed onto our metal catalyst, we will then see that there's an interaction between the hydrogens and the pi bonds. And those hydrogens are going to insert themselves into the pi bonds, and then we no longer have the pi bond, it will break away from our metal surface. So initially, we would have our first carbon atom interact and attach to the hydrogen, so the hydrogen will replace the pi bond, while the other pi bond is still adhered to the surface and can interact with the other hydrogen atoms that are there. So they will add one at a time, and we will see once both of the hydrogens have added, they are both going to add to the same side, that is our syn addition, because there's no time or chance for there to be any rotation around the carbon-carbon bond for us to have an anti-addition of those hydrogen atoms. So they will always add to the same side. And again, once there are no more pi bonds on the carbon or p orbitals on the carbon, it will no longer interact with the metal catalyst. It will be released from the surface, and we will have our alkane. So now let's look at our alkynes, where we will have two pi bonds between our two carbon atoms. We will see a very similar process because we still have those p orbitals and our pi bonds. With our alkynes, we will need to use an excess of our hydrogen gas, since we are dealing with two pi bonds. And if we have that excess, we will see once again that we will convert all of our pi bonds into sigma bonds, and we will see syn additions. It will happen in a two-step process, so we'll have an alkene intermediate, which we will then add the second pair of hydrogen atoms across it. So both hydrogens will add in a syn addition across our alkyne. If we do not have excess of the hydrogen gas, we will see a mixture of both alkenes and alkanes within our reaction mixture. So again, we need to make sure that we have a large excess of the hydrogen, since we will need to add two hydrogen molecules for every one triple bond. And again, if we don't have that excess, we will see a mixture of alkanes and alkenes in our reaction flask. We can stop our alkynes at an alkene with what we use as a poisoned catalyst. A poisoned catalyst is just a catalyst that has a decreased catalytic ability. One of the common catalysts that we're going to see in this process is Lindlar's catalyst. And the Lindlar's catalyst, if we use it with our hydrogen gas, will stop the hydrogenation process of an alkyne at the cis alkene. So our Lindlar's catalyst is going to use palladium mixed with calcium carbonate and also a little bit of quinoline. And again, this compound that I have drawn on the screen with our two rings connected together is quinoline. And it is a mixture of all of these compounds that generates Lindlar's catalyst for us. And again, it will stop the hydrogenation of our alkyne at the cis alkene. So if we look at our reaction of our alkyne, if we have our hydrogen mixed with Lindlar's catalyst, and you will either see in the arrow Lindlar's catalyst, or you may actually see the compounds drawn out with the palladium and the calcium carbonate and the quinoline. And the key is it will not hydrogenate all the way to the alkane. We will stop at the alkene, and specifically, we will generate that cis alkene.